stuff. Okay, so feels like quite a while ago because with 4 days, so last Tuesday we were talking about the sun. So just as a bit of review, we were kind of focused on the outer layers, the atmosphere of the sun, but we did briefly discuss the interior. So we have our kind of layers of the sun's surface, the photosphere, which is what we see. Sorry, trying to make sure I got everything open. With photospheres, which we see, so that's where photons can escape the surface of the sun. There's not, we call it the surface, but there's not really a surface there. There's nothing solid. The sun is a big ball of plasma. If you passed through the photosphere, you would not notice a difference between the edge of the photosphere and directly inside of it. But it's the photons do notice a difference. It's where photons can escape the surface. So light can escape the photosphere, it can't escape within that. So that's what we see. It's where sunspots are, those darker areas that are still very, very hot, just not as hot as the rest of the photosphere, which is at about 6,000 Kelvin. Above that, we had the chromosphere, which was that red layer where we saw filaments and plages, which were kind of our first indication that the surface of the sun, everything we see is going to be kind of dominated by the magnetic field lines, magnetic fields generated within the sun. That layer is mostly, when we observe it, we look at the H alpha, so a hydrogen emission line that is red, that we see coming mostly from this slightly hotter layer in the sun's atmosphere above the photosphere. The next layer above this is the corona. So this is a layer of the sun we pretty much never see except during solar eclipses when the moon blocks the sunlight, so we can see the very hot but very low density. So low density means it's also not very luminous material surrounding the sun, which is the corona. So 1 million Kelvin, 1 million-ish degrees Celsius, very, very, very hot, but very, very low density. And this is also where we see a lot of the solar activity in the form of prominences and flares and those halo streamers that, again, we talked a little bit about last week. Just as one last little kind of reminder before we get into some more newer stuff, we also saw the sunspots, and just kind of all of this solar activity really has to do with these magnetic field lines. So sunspots happen where magnetic field lines come through the surface and they hold that solar material at the surface, allowing it to cool to, you know, a cool temperature of 4,500 Kelvin, around 4,000 degrees Celsius, so very, very, very hot still, just cooler than the rest of the material. And we were also able to, by looking at the sun's surface, we were able to notice that the sun's interior layers travel through convection. And we know that because we see granules on the surface of the sun. So we can see the surface of the sun is kind of boiling. And that's convection. We know how energy is transported, and we're going to use that to tell what's happening inside the sun. So that's a really quick run through of what we discussed last Tuesday. Does anyone have any questions before we jump more into some of that solar activity in the corona? Awesome. Well, let's just move right ahead. So I think we might have very briefly touched on this. I might have showed this video, but another form of solar activity, solar weather that we can see are coronal loops, which are loops of ionized material that get trapped in magnetic field lines. So when I say ionized, what I mean is that electrons have been stripped from the atoms. So if you bump into an atom hard enough, either with a photon or with another atom, you can cause one of its electrons to go flying off, and you end up with a positively charged ion and an electron. So if this is hydrogen, where there's only one electron, if you ionize it, you'll end up with one proton and one electron instead of one hydrogen atom. With heavier elements, things like oxygen, carbon, they can be ionized multiple times because they have multiple electrons. So if you bump them hard enough, either a photon hitting it or another atom hitting it, it can lose an electron or lose multiple electrons, and you end up with charged ions, positively charged ions, as well as a bunch of negatively charged electrons. So when I say ionized, that means positively and negatively charged particles. Because the sun is so hot, there's a lot of things bumping around. There's a lot of highly energetic photons. And as those bump into the elements within the sun, the atoms in the sun, we get ions, positively charged ions and electrons, which can get caught in magnetic field lines. And we can see these cool coronal loops and solar flares and other activity. Because there's a lot of material in those loops, we can actually sometimes see them even though they're close to the surface of the sun, because they're going to be brighter because they're more dense than the rest of the corona. So there's stuff trapped there, it gets more dense than the rest of the corona, and it gets bright enough that it's actually observable briefly. We can also get very dark spots in the corona where there are coronal holes. So the coronal loops were closed magnetic field lines. So the magnetic field lines burst through the surface and they come back down. So maybe where we would see sunspots. But there can also be places where the magnetic field lines don't come back. They just kind of explode out. And that will let material start streaming out of the sun. So charged particles will flow out of the sun. This is where we get the solar wind, which we'll talk about in a second. But in the corona, they appear as dark spots because there are going to be places where the density is even lower. So the density in the corona is already ridiculously low, much lower than the, like 10, I think I said 10 to the negative 8 times the atmosphere of the Earth last class. So it's already really low, but in these corona holes, it's going to be even lower because there are no magnetic fields holding it in, and it's all escaping out into space. So charged particles, ions and electrons are escaping into space, moving through something we call the solar winds. Kind of extreme examples of this are coronal mass ejections. So if you have a bunch of magnetic field lines bursting through the surface of the sun, you can trap a lot of those ions, so a lot of these charged particles. And if those magnetic field lines eventually burst and become a coronal hole, so we go from a loop to a hole, you can get a huge amount of material ejected from the sun over a period of a few hours. So these disrupt the flow of the solar winds. We get a lot more material for a very brief period of time flowing out of the sun. They can send up to 2 trillion tons of material into the solar system. So one coronal mass ejection can eject 2 trillion tons of material from the sun, which is kind of crazy. And these things are also highly energetic. So if these coronal mass ejections are coming towards us here at Earth, they can produce kind of crazy geomagnetic storms, which will generate beautiful aurora. So we get really intense aurora at the North and South poles, also sometimes coming down into lower latitudes. But they can also disrupt electric systems. So in the 1850s, there was an event called the Carrington event, where there was a big coronal mass ejection that moved towards Earth and actually caused telegraph machines to short out for a brief period of time. Some of them started sparking and caused fires, but there was a whole huge issue with this coronal mass ejection actually disrupting the communication systems on Earth back in the 1850s. Now in the 1850s, there wasn't a huge electrical grid. Now there is. So if a coronal mass ejection hit Earth now, it could cause serious blackouts and actually be a pretty big problem. So if you want to learn more about this, I'm going to be sending out a podcast about coronal mass ejections and how we can prepare for them soon that you could listen to as a podcast project. So if you need even more doom and gloom in your life, sorry, but luckily there isn't one happening right now. But as we enter a period of increased solar activity, which we will soon. There could be a coronal mass ejection. It is a possibility. Sorry, there's a question. So this image is I think the question is about why don't we see a dark spot in this image? And that's because this is a slightly altered image. So we would expect to see a coronal mass ejection and then a dark spot where the stuff was flowing from. We don't see that because this is kind of a fake image where they put a picture of the sun above the coronagraph, which is a mask to block out the light from the sun. So normally we can't really observe the corona. So in order to do that, we put a mask on our telescopes that blocks all the sunlight so we can see the corona, the lower density material around it. And so to make this pretty, the people who made this GIF put an image of the sun in front of that. I don't think that's an accurate image of the sun during this coronal mass ejection. So I think that's why we don't see a dark spot here. You would eventually, if you were measuring the corona after this mass ejection, you would see a dark spot where the material flowed from. But during the ejection, it will be very bright as the material is denser there. Hopefully that helps. Awesome. Okay. So on that note, I know I kind of talked this up last week, but today we finally get to save our astronauts. So we're going to pause here and do an activity. So on Canvas in your assignments, this is going to be day 10, hopefully, I think. I should have checked, sorry, yes, this should be day 10. So if you click on that, there's a link to a quiz called Save the Astronauts, where your goal is going to be to figure out when a coronal mass ejection reaches Earth. So I've given you some images of a coronal mass ejection coming out of the sun with a scale, as well as you can see here, just really quickly to make sure you can see this. There's these times for each of these images. So we're going to find how far the coronal mass ejection has traveled as a function of time. That's our kind of goal. So we can tell the astronauts on the ISS when the coronal mass ejection will reach Earth and when they should not go outside in case there's a malfunction with one of their spacesuits, which could happen if a coronal mass ejection was coming towards them. So we're going to just give them a window of time when they should stay inside the ISS, stay nice and safe. So you're going to measure those distances, plug them in here, and then you're going to make a graph that should look something like this, where we have time versus distance from the sun. And we're going to try to find the slope, which is going to tell us how fast the coronal mass ejection is traveling. So that is going to be your group's goal. There's hopefully the answers to this one are more right than the Jupiter spot. So when you submit answers, they should actually tell you whether or not they are correct. I'll point out if you do graph in sheets, you can also graph just on paper. Sorry. You can actually get a slope, which is going to be one of the things I asked for, by right-clicking and selecting series, and then you'll see over here you can add a trend line, which will tell you the slope. So that'll be something you'll want to get, but you can I also tell you how to just measure a slope if you just drew it. And there's one other question before I put you all in breakout rooms to work through this, and that is I will post that podcast in an announcement. That's my plan. So as I am uploading this video, it will go in an announcement and get blasted out. So let me open up some breakout rooms. Any questions actually before I send you off to save some astronauts?
To find slope, can we still use like y mx equals mxb?
Yep. Yep. So if you
My one question is, which one's the important one, the m or the b, for like, because like y and x are obviously y and x. I can't remember what the other two do.
Awesome. So in a line, y equals mx plus b, the slope is going to be that m. So b is where the line crosses the axis. Sorry, I can't see this, but so what we're really interested in is it's going to be the 6.17. The 10.9 doesn't really matter. We just want to know how fast it's traveling, which is going to be the 6.17, your m in your slope, which if you just drew this over on a graph, you could also find that by saying, okay, this traveled about 30 millimeters in 5 hours. 30 divided by 5 is about 6. So that would be how you would find a slope without finding a trend line. You do delta y over delta x, change in y over change in x. But my instructions do walk you through that as well.
Thank you.
Any other questions? Great. Let's save these astronauts.